Hi, I think we're taping. Sorry about that. You're not supposed to have pop-ups right when you start a video. We are in section 5.2. I hope you're there now. I know it's coming back from break and it's been a little bit tough, and homework set 3 is a little hard, but here we are, and the homework doesn't cover Poisson, so you won't see a Poisson in this homework. Of course, those are my dogs, exactly when I'm going to start. We're on page 68, and this is a new random variable. So hopefully what you realize in chapter 4 are we have these things X called random variables that take on random values, and they have probability associated with them. And then when we have a random variable, we have things like the expected value of the random variable. That was in chapter 4. That's on average, what value does a random variable take on? And we also have the variance of a random variable. How much spread is there of the random variable about the mean? So once we define a random variable, there's things we can find out about that random variable. And in section 5.1, we learned there's lots of special kinds of random variables. And you learned 2 of them in chapter 5.1. One of them, probably the easiest of the random variables, is the Bernoulli. And then in chapter 5.1 was also the binomial. So it's not until section 5.2 now you see this is your third random variable. And random variables, they're just, what we're trying to do is classify them into groupings. So when you see a type of problem that says, hey, I'm going to go down to the gym and shoot 10 baskets, and what's the probability I make 5 of them? You go, oh, that's in the form of a binomial. You're going to do something n times and count the number of successes. So Poisson has a story too, and what we've been doing in chapter 5 is just kind of making the stories for some of the most common random variables, and that brings us to Poisson. So Poisson is a person. Actually, he was French, and that's not surprising. And he's known for saying life is good for only 2 things: to study math and to teach it, which I have to agree with him on that one. Poisson random variable was originally created as an approximation to the binomial distribution. So Poisson came after the binomial as a way to say, hey, if I have a binomial variable that has certain qualities, in other words, something with a really small p and a large n, this is a nice approximation. I'll show you what I mean. But a Poisson random variable is the probability of something happening over space or time or region, where sometimes that thing that's going to happen it rarely happens, which Poisson's not always that, but it can be that's what makes it a good approximation to the binomial. So for example, you have a whole textbook or you have a manuscript. The number of misprints in a manuscript, you have many pages. If you have one that's been looked over, and it's Dr. Grimaldi 10th or 11th or whatever edition of his text, you're not going to find very many misprints. That would be a rare occurrence. Number of wrong numbers. When you think of all the numbers that come into the Rose-Hulman switchboard every day, there's probably not too many wrong numbers. Number of car accidents. Even in, Terre Haute, there's not that many for how many people are driving, how many cars are out there. Number of stars in space, all kinds of things. One of my favorite, I always wanted to kind of do this, is animal litter. I know that sounds strange, but I have a huge backyard. I have a new house. I have 4 dogs now, so you can imagine there they are. But in the yard, we call it poop patrol. It's kind of gross, but every once in a while, well, before I mow the grass, I go out and clean up all the areas so I don't mow over them. And I only have to go a couple of days before the lawn is pretty full, but you can see that it's very strange. There's pretty much random scatter, but you could pick an area. It is true, kind of maybe not for dogs, but over by the fence. I don't know why my pen's not working now, but over by the fence, you'll maybe see a clump there and a clump there. But pretty much if you broke this up into a big matrix, you would see an average number per little square, and I think that's kind of interesting. So let's this is just a simulation. Oh, I don't know why my pen's not working. I might stop for a minute to figure that out because it's getting hard to write. Let me stop it right. Well, I don't know why my pen's not working. I'd like to make a joke that it's out of ink. I'm still trying with it, so I really don't need, well, let's, oh no, sorry, it's a homework question. Yeah, it's just not writing. So for some reason, I can write with my, you can see right here, I can use my mouse, but I can't use my pen. Well, I gotta keep going, so we'll worry about that later. This I really like as a display of why we're using a Poisson. So imagine really how a Poisson is derived from a binomial. Imagine you took this huge square. I mean, imagine this is a dartboard that you're gonna put on your wall, okay? And it's pretty big, and what it is a 10 by 10 dartboard, 10 foot by 10 foot. I'm going to break up all the little squares into 1 foot, 1 foot by 1 foot, all these little grids. So I have 100 little boxes in here, and I'm going to throw 400 darts just randomly. So imagine you're over here. This is hard to draw with a mouse, and you have some darts, and maybe you have maybe a machine that shoots them, and all these darts come flying out, right? And they're going to land on this board, okay? And if you have no skill, you're not trying to hit anything, you're just randomly throwing them all over there. What we can imagine, if this was a binomial and we let x be the probability, or x be the number of hits in one of these boxes. So let's choose like a box right here. What's the probability I have x dart hits in this box? Could be that none of them are there. It could be all 400 are there. The probability I'm going to hit this if I randomly throw, since it's a 10 by 10 space, and there's 100 of them, is 1 out of 100 that I'm going to hit that space. So out of 400 trials and a 1 over 100 chance of hitting it here, I would expect on average there to be about 4 dart hits in there. And if I looked at this one over here, another thing, I mean, there's probably, or I would expect 4 dart hits to be in there. And we know expectation isn't reality necessarily. I mean, some of them might have none, 1, 2. I mean, maybe this one up here only got 3 hits in it. I mean, maybe the one down here has no hits in it. But if I took all these boxes and did an average, on average there would be 4 hits per box. And what I'm going to do is use that average or that rate of 4 hits per box, and that's how we make the binomial. I mean, how we make the Poisson. What we're doing with the Poisson is really taking the rate of the binomial, and that becomes that parameter lambda in our Poisson. So here was Poisson's discovery. He said, let the random variable x represent the number of successful dart hits in a randomly selected square, like we were saying. The probability the square has x hits in it, where x could be 0, 1, 2, 3, 4, up to 400. And we're letting the probability of success be 1 over 100, and the number of trials is 400. So we're going to write this as a binomial first. So probability x is equal to x is just, this is your binomial from section 5.1. Number of trials, 400. Probability of success, 1 over 100. Probability of failure, 99 over 100. All I'm doing is writing this in its factorial notation. And then I'm going to do a little bit of magic here. I'm not doing anything that's illegal. I'm just rewriting a little bit of maneuvering here. So I'm going to take, see these two terms right here? I'm just going to cut, if I did 400 factorial divided by this, that's what the numerator is right here. All it is this is going to go all the way down to 400 minus x plus 1 when I actually divide the two. Here's the x factorial. It's just going to there. There's the 4 to the x. You see that guy right here? He's just going to there. I guarantee you I'm putting somewhere and everywhere. There's no trickery here. This is 400 to the x. I'm putting it down here. I'm breaking this up into 2 pieces and making a top and bottom of a fraction. The 400 goes on top and the x goes on the bottom. Is this just a day for emails or no video making? Anyway, so if I simplify all this, we can imagine for any x, I'm going to say this is approximately 1. Okay, so there's takes care of that. 40x over x factorial, there's nothing I can do with that. This down here, this is really, really small. That's why we need a large number of trials, small probability of occurrence. This is going to be close to 1. Even raised to the x is close to 1. This right here, you might remember this as a limit from calculus. A limit of 1 minus 4 over x raised to the x power is actually e to the negative 4. I realize we're only going to the 400 here, but if you took this thing to infinity, this is what you'd get. So here is a nice approximation to this original binomial that was right here. Somebody commented on my videos from another country or somewhere and said, you know, we like your videos, but you got a little bit too much scribbling, and I'd have to agree with them on this one. It is very much scribbled. So, what have you learned? We can approximate a binomial with a Poisson. And if you take the mean of a Poisson, it actually becomes, I mean, of a binomial, it actually becomes the rate function in a Poisson. So probability x equals x, you hit x darts and a spot. It's given by e to the negative lambda, lambda to the x over x factorial. Lambda is that mean that we got from the binomial. And so there's a function. It goes from 0 to infinity. Sometimes that's not realistic because you know we only threw 400 darts. So, but we need it to be valid. So for that, it needs to go to infinity. Even after the first several, I mean, if you expect 4 hits, once you even get to 100, there's almost zero probability there. So I feel like I'm already probably getting long on this one, but so there's officially the density function for a probability function that's Poisson. All I'm showing you right here is that that function is legal, and I hope you remember what it means to be legal. This thing right here, right, has to sum to 1, and it has to be positive. Definitely is positive because everything in it's positive. And I'm just showing you down here with a little help from the Taylor series that you also did in calculus that this guy sums to 1. Again, I did some fancy maneuvering, but definitely he sums to 1. Here I'm just doing a practice problem. I'm converting, I'm starting out with a binomial and showing you how I switch it to a Poisson. I think it's really slick, and down here I'm showing you how close the approximation really is. That's very nice. Even I didn't even have that big of n and small a p, and I still get a very good approximation with the Poisson. So that's what I was trying to do then. Again, here's another binomial to Poisson. Here's another binomial to Poisson. This gives the mean and the variance of a Poisson. So here I'm just deriving the mean for you. But the mean of a Poisson is lambda. Lambda is the rate. If I expect 4 dart hits per square, then how many dart hits do I expect? I expect 4. It's kind of like circular there. And nicely, and I didn't prove it, maybe it'll be a bonus somewhere, the variance of a binomial is also lambda. So it's a pretty nice clean function. Really nice example from World War II. This is a true story how it was the American statisticians, I think, that were trying to approximate how many bomb hits were expected in a certain area during World War II. They blocked off London into a bunch of square grids, kind of like that original problem. It's just seeing how good the approximation is between reality. This is what really happened in World War II, and here's what they could approximate with a Poisson. What they were trying to see is if in London, the Germans, if they were randomly bombing, or just, I mean, or if they could direct a bomb to a certain area, and what they determined is they could not direct the bomb, actually. It was just random. Wow, I never get this many emails. And I guess my only warning about a Poisson, I put it right here, is you always have to put lambda on the same interval as your problem. So, for example, up here, I'm letting x be the number of customers that come to McDonald's at a rate of 4.6 customers per hour. Okay, if later I change and say how many customers do I expect over a 1.5 hour time period, I have to adjust my lambda to be on a 1.5 time period. If I give you a problem starting out, this is how many accidents per week, but if I ask you about accidents per day, then lambda has to be on a per day schedule. I mean, that's the one thing you can do wrong with a Poisson, is that you don't convert to the same time frame. The lambda has to be on the time frame of the problem itself. So sorry, this is going to be a little bit long, but oh, yuck. Okay, I'll talk to you later.